I'd like to thank MSI and Marcy for the opportunity to talk about some progress we've made in developing a 3D model of this San Juan and Silverton Caldera Complex. Yeah, I'd like to acknowledge our collaborators. I'm Doug Yager, I'm a geologist. I have a long history here in the basin working on geology here. I feel really fortunate to have had that opportunity. We also have Bruce Smith and Maria Despan. They're research geophysicists. They're senior research geophysicists. So we have a lot of support there. Brian Rodriguez, he's the magnetotelluric data project chief that I'll be talking about later on in the talk. We have Eric Anderson, and his specialty is the magnetics and also 3D modeling. And we have the collaboration with Water Science Center with Rob Runkle and Katie Walton Day. And Tom Castoval, who you've heard is an expert in the field down here, and we're lucky to have him just a few doors down from my office to ask questions about. We also have a great team of collaborators, land managers, Ben Martinez with the Forest Service, representing the EPA. We have Rebecca Thomas, Ian Bowen, and Steve Diamond, and we're lucky to have Lisa Richardson with the Bureau of Land Management, and Kirsten Brown, who many of you may know has done a lot of the 3D modeling of the mine tunnels down here. So we want to build on Kirsten's work and extend that into the surface with more geology. And the Animas River Stakeholders Group that has just done a fantastic job down here since 1996 when it was formed. So today's outline, I'm going to talk about the geologic and geophysical data inputs to the 3D model. And then I'm going to talk about 2018 processing that we've done on legacy electromagnetic and magnetic survey data, and show some preliminary conductivity depth profiles. And then I'll talk about new data that we collected here in July of this year. And that's the audio-magnetotelluric data and the magnetotelluric data. And we're imaging into great depths into the caldera with this MT data. And then we have a proposed new state-of-the-art electromagnetic time domain survey that we put in for point of award this year. And I'll show an example from Crested Butte. So here we have a familiar, where's the pointer on it? Oh, there. So here we have a nested caldera complex. We have an older caldera and a younger caldera. The older caldera is the San Juan caldera, so we have a super volcano and a Superfund site. This erupted 1,000 cubic kilometers. So put it in perspective, there's 0.8 cubic kilometers erupted from Mount St. Helens in 1980. This erupted 1,000 cubic kilometers. So nested within that, we have the Silverton caldera, and that erupted about 50 to 100 cubic kilometers. And the reason I mention this is that when these calderas form, it's basically a collapsed volcano. So the roof of the volcano founders in to the void that was caused by when this magma erupted along these ring fractures here, which are delineated by Mineral Creek and the Animas River, kind of a semicircular pattern of the caldera. And these blocks drop in several kilometers when they erupt. Later, lava's filled in the caldera system, so these rocks in kind of a salmon color here, those are lava flows that infilled the caldera. And then the new magma came into the caldera, it domed the caldera and formed a graben system. It was highly mineralized. That's known as the Eureka graben, and that's here. And then there were intrusions that formed along the ring fracture zone that were zones of weakness. And these areas in red were late stage intrusions that were also drove hydrothermal systems and mineralization. So the reason I'd show this is that we have an incredible natural laboratory to basically try to do a better job of imaging the subsurface geology, the lithology. We also have, again, at the surface, we have a really detailed alteration map of the surface. So we were talking about background. Well, each of these basins are affected by different alteration types. The rocks in green make up 88% of the watershed, and those are important because they have some acid neutralizing capacity. And the reason is there's calcite in certain places throughout the caldera that can neutralize some of the acidity and perhaps neutralize some of the acid rock drainage and also the acid mine drainage. Those brighter areas in the caldera are areas of intense alteration that overprint and obliterate the acid neutralizing capacity and generate net acid production. So depending on what basin you're in, such as this Mount Molly area draining into the middle fork of the Mineral Creek, most of that is acid generating alteration. It generates a lot of metals, and so that's a natural source that's going to have to be dealt with. And in this area, in the South Silverton mining area, you have a lot of propylitic alteration, so you have more circumneutral waters in certain places. So depending on where you are, the baseline is going to be impacted from these different alteration assemblages and mineralization. So we know pretty well about the surface. And we also have really good exposures of the bedrocks because of the high relief of the mountains here, and then also the weathering that has exposed the mineralized systems in the rocks. So what we want to do is be able to look inside the mountain block into the subsurface. And here it's a little bit hard to see, but we've draped the alteration on a terrain. This is Cement Creek down here. Here's Prospect Gulch. Gladstone is just off the map. And we're looking west across Cement Creek. And so all those alteration assemblages, you can see the bright areas are net acid producers. The green is acid neutralizing capacity. And each one of these basins has different water quality at the surface because of the water rock interactions along those flow paths and also groundwater. And so what we want to do with our study with the geophysics is we want to look inside the mountain block. And so we have a cutaway, a diagram here that shows the different types of things that we're thinking about. And this kind of ties in with what Rory had shown yesterday. So we have a highly fractured carapace at the surface. We have superficial deposits. We have a shallow groundwater system and a deeper groundwater system and a paleo groundwater system that could represent the old hydrothermal system that had that basically was brought up the minerals that were deposited along these polymetallic veins shown in yellow and red. Some are mineralized and some are barren, just with the yellow here. We have intrusions with brecciated margins. We have chimney ores that were mineralized in the Red Mountain District. And so we have mine workings that we intersect the groundwater system, short circuit it, and then we have surface point discharge here to the stream. All right. And so with the geophysics, we want to be able to look inside the mountain block and see if we can better characterize the geophysical signatures to help understand the subsurface, the groundwater flow paths, and also at the local scale and also kind of the bigger picture scale of can we use our information to help us understand mineralized systems better. So we have kind of a twofold, kind of a big picture type of a focus and also more narrowly focused to identify groundwater flow paths using the geophysics. So what we've done is we've flown this legacy helicopter electromagnetic survey, HEM, and we have a helicopter with a bird down here that it tows, and there's a transmitter and a receiver on that. The transmitter transmits a current which has a electromagnetic field, and then a secondary electromagnetic field interacts with the subsurface material, and depending on the strength of that secondary field, then that's related to the conductivity of the rocks in the subsurface. With magnetotelluric data, we use natural fields. So we use the charged particles from the sun, and then we also use lightning. And so I was thinking about this, that, you know, lightning is not my friend when I'm standing on a ridge doing geology, but to the geophysicists, that's great, because the more lightning, the better the signal for the MT. So here's block diagrams of the HEM, the helicopter survey. And you can see these are flight lines here, north-south, and they were 200 to 400 meters is when we flew these in 1999. And then the signal is converted to a conductivity. The areas in red are high conductivity. And with a time domain survey, well, this was a frequency domain survey, so it records at multiple frequencies. A time domain survey is where you switch the transmitter off, and then you measure the decay and the secondary electromagnetic signature from that secondary field, and then that is converted to conductivity. So there's advantages of the time domain survey, and I'll talk about those later. So here's our MT crew with Brian Rodriguez here and Eric Anderson. They're installing a coil here. And this was a real collaborative effort with Lisa Richardson. She participated in the MT survey. We had students from Fort Lewis College, from Bozeman, Montana, and from Western State College. So it was great to have Brian there to teach them about this MT data collection, and they all helped with the installing the equipment. So with the MT data, you have to measure the electric and the magnetic field at the same time, perpendicular to one another. So that's what this portrays down here. So I wanted to talk about the depth of penetration and the resolution of these two methods. So with the HEM data, you see shallow, tens of meters, but it's higher resolution. With the natural field AMT, you see deeper to a kilometer, but with lower resolution. And then with the MT, you see deeper. So in building the 3D model, you put all these different parts together to build the full 3D picture from the surface down to depth. And basically what we're measuring is the conductivity of the rocks in the subsurface. And each of these are all different rock types. These are conductive and these are resistive. There was a relationship with 1 over R. Conductivity is inversely proportional to the resistivity. So small resistivity have high conductivity. And we're dealing with a lot of volcanics, so you get kind of intermediate conductivities. And here's an important relationship with groundwater flow paths. So there's a direct correlation between total dissolved solids and conductivity. So basically, if you have high dissolved metals in the subsurface, that would be a permissive that you would have a high conductivity in the geophysical signature. So now I'm going to show you some examples from our legacy HEM data where we've reprocessed that data to do those conductivity depth profiles. And I'll show you one in Lower Cement Creek here, and then one at Chattanooga Fen, and if time permits, the Upper Animas. So on the upper right, we have the old survey data that's shown in this colored ribbon that's draped along Mineral Creek. And this is draped on a terrain image. And these green sticks that are here are from the tracer studies that Rob Runkle, Katie Walton-Day, and Brian Kimball had done back in the Animas Abandoned Mineland study days. And the stick height is proportional to the groundwater inflows. And these are also correlated with geochemistry that we have from these inflows. So you can see a whopping high 27,000 micrograms per liter iron. And the stream water inflows 2390. Similar stream water iron concentrations here, but lower inflows here. So on the lower diagram, we have a conductivity depth profile. So we're seeing it 100 meters below the surface. And what I want to point out is with this type of new processing, we can resolve where we have a groundwater that's fairly high high conductivity that merges with the surface high conductivity. And here we have a shallow groundwater system that has high conductivity, and then a deeper system that has high conductivity. So here's the example from the Chattanooga Fen. Again, this is a conductivity depth profile, and R is resistive and C is conductive. And this area around the fen has a high resistivity signal. And these are preliminary profiles, preliminary interpretations, but one interpretation is this is a dilute inflow that is a little bit more resistivity than, a bit more resistive than these areas down at depth. Here's some other more resistive or more dilute resistive areas that perhaps relate to these inflows. Okay. So now I want to talk about the MT data, and these areas in orange dots are stations, and we've collected all these data in orange, and we've designed them to cross the structural margins of the calderas and also cross the graben in the mineralized areas. And this is what we have planned for next year in the Raster Gulch. And I'm going to show you an example from the northwest part of the caldera. So we're pretty excited about this because we didn't see everything that was just resistive. You know, there are changes here. So this goes down to 600 meters. So we're seeing deeper than the HEM data. And we cross a caldera fault. And you notice this resistive block is downdropped as a normal fault from this other resistive block to the west. And then we have a conductive zone that's in the vicinity of one of those chimney ores and also a dacite intrusion that's nearby. So we're seeing heterogeneities in the MT that perhaps correlate with the geology. So we're pretty excited about this. And these are blocks from a proposed HEM time domain survey that we had requested as point of award. And so the way this differs is that these blocks, they don't just go north-south. We contour around up drainages, up the primary streams, and into specific drainages of interest, such as Chattanooga Fen, Ross Basin, Eureka Gulch, Raster Gulch, South Fork, Mineral Creek, Middle Fork, Mineral Creek. So we want to work with collaborators to identify those priority areas of interest. And this is the type of result. And what I want to emphasize is this goes down to 300 meters. So we're basically doubling the depth of observation with this type of survey. And there are other beneficial. It's the state of the art. There's new GPS now. There's higher resolution, and we can identify lithologies at depth better. These are all different lithologies that are being mapped by the time domain survey. And so, am I done? Okay. So if anyone wants to hear about what we have planned and you know, for the future, please talk with me later. But thank you.